This manual describes the Byzantine fault-tolerant consensus engine, a distributed agreement protocol designed for networked systems requiring strong consistency guarantees. The protocol operates on a message-passing model across heterogeneous node topologies. All processes maintain a local state machine and communicate via asynchronous channels with bounded delay. The system assumes that fewer than 1/3 of nodes may behave arbitrarily at any given time. Each participating node runs 3 concurrent phases per consensus round: proposal generation, vote aggregation, and commitment verification. The proposal phase selects a leader via deterministic election based on round number and node identifiers. The leader node constructs a candidate value from pending client requests and broadcasts this proposal to all followers. Nodes that have not yet received a proposal for the current round enter a waiting state with a configurable timeout interval. During the vote aggregation phase, each node independently validates the received proposal against local state invariants. Validation checks include cryptographic signature verification, sequence number ordering, and absence of conflicting pending transactions. Upon successful validation, the node appends a signed vote message to its outgoing queue. Nodes accumulate votes from peers and maintain a vote counter in memory. When the counter reaches the quorum threshold of 2/3 plus 1, the node transitions to the commitment phase. The commitment phase requires a node to have received qualifying votes from at least 2/3 of the total peer set. Upon reaching this threshold, the node generates a commit message containing the proposal hash and round number, then broadcasts to all peers. The node also writes a commitment record to its persistent write-ahead log before applying the proposed value to its local state machine. This ordering ensures durability in the face of node failures or network interruptions. State machine application follows a strict sequential order. Each confirmed proposal contains a monotonically increasing sequence number assigned by the leader. The state machine applies proposals in sequence, skipping any number gaps and buffering out-of-order proposals until gaps are filled. Application triggers execution of the embedded transaction operations against the node's local data store. State changes are not externally visible until after the proposal has achieved consensus and been committed to the persistent log. Leader election occurs automatically at the start of each new consensus round. The election mechanism uses a round-robin scheduling based on the current round counter modulo the total number of eligible nodes. This deterministic approach eliminates the need for additional election protocols while distributing leadership evenly across the peer set. Nodes update their leader index locally without inter-node communication. If the designated leader node is unresponsive, a view change protocol activates after a fixed timeout period. The view change protocol implements leader failover when the current leader has not produced a valid proposal within the timeout window. Follower nodes broadcast view change messages to initiate consensus on the next leader. These messages include the node's current view number and its highest committed round. The new leader collects view change messages from a quorum and constructs a proposal that advances the consensus state beyond the previous round. View change operations do not affect pending client requests, which remain queued in the proposal buffer. Network message delivery is assumed to be eventually reliable, but may be delayed or reordered. The protocol handles duplicate message reception by tracking message identifiers and sequence numbers at the receiver. Duplicate votes and commits are silently discarded after verification. Similarly, out-of-order round messages are buffered in round-specific queues and processed when prior rounds have completed. The protocol does not require an order message delivery from the transport layer. Node state is persisted to stable storage at designated checkpoints. The system records the current view number, the highest committed round, and the most recent state snapshot at regular intervals. The checkpoint interval is configurable and defaults to every 100 committed proposals. Checkpoints enable rapid recovery when a node rejoins the network after unplanned shutdown. Upon restart, a node loads the most recent checkpoint and resumes consensus participation from that point forward. Client communication with the consensus system occurs through a client library that maintains connections to one or more peer nodes. The client submits requests to a node via a simple RPC interface specifying the operation and its parameters. The node accepts the request and buffers it in the proposal queue. Once a consensus round completes and the request has been applied to the state machine, the node sends the result back to the client via a callback or response message. Latency and throughput characteristics depend on cluster size and network conditions. Consensus rounds proceed in approximately 2 to 3 message delays under normal operation. The minimum round time is the network round-trip latency multiplied by 2. Throughput is bounded by the proposal rate that the leader can generate and by the rate at which nodes can apply confirmed proposals to their state machine. Typical deployments achieve committed proposal rates between 1,000 and 10,000 operations per second. Byzantine fault tolerance guarantees that the system will maintain consistency even when up to 1/3 of nodes behave maliciously or fail arbitrarily. The protocol ensures that all non-faulty nodes commit the same sequence of proposals in the same order. This property holds even if faulty nodes send conflicting messages, forge cryptographic signatures, or cease responding entirely. The consistency guarantee holds as long as the Byzantine nodes remain fewer than 1/3 of the total peer set. Message authentication uses cryptographic signatures to verify sender identity and prevent forgery. Each message includes a signature computed using the sender node's private key. Receiving nodes verify the signature using the sender's public key, which is distributed during system initialization. Nodes maintain a keyring file containing the public keys of all authorized peers. Messages with invalid signatures are rejected immediately without further processing. Configuration parameters are read from a static configuration file at node startup. Key parameters include the peer node list, timeout intervals for proposal and view change phases, checkpoint frequency, and cryptographic key paths. The configuration file uses a simple key value format with one setting per line. Nodes do not reload configuration during runtime. Configuration changes require node restart. The configuration must be identical across all peers to ensure consistent leader election and quorum calculations. Monitoring and diagnostics provide visibility into consensus operation. Each node maintains internal counters for rounds completed, proposals rejected, view changes triggered, and messages received. These counters are exposed via a metrics endpoint that exports data in a structured format. Operators can query this endpoint periodically to observe cluster health. High view change rates indicate leadership instability, while high rejection rates suggest network partitions or Byzantine behavior. This concludes the Byzantine fault-tolerant consensus engine specification. The protocol provides strong consistency guarantees for distributed systems requiring fault tolerance. Implementations should follow the message ordering and state machine application rules precisely. Deviations from the specified behavior may result in safety violations or liveness failures. Refer to the appendix for detailed message format specifications and pseudocode algorithms.